now I'm going to go back and look at problem 434 a little bit because just about everybody's turned it in. And in this problem you had to do two functions. One was a factorial function, which most people chose to do it recursively, just like the example in the video. And the other one is you had to make a function that approximated the series expansion of the cosine function. So this is the cosine function, and you can approximate it using this series expansion. So not everybody is in trig or calculus yet where they cover this subject matter. I don't remember which level it gets covered in. But what you find out, and you can see the pattern, is that the more terms that you add here, the more accurate this function will get, this approximation to cosine x will get. But it also turns out that if you find the cosine of some large number here, so a large number of radians, and this has to be in radians, and recall that 2 pi radians equals 360 degrees. But it turns out that if you put in, here I'll write that, 2 pi radians equals 360 degrees, and this number here has to be in radians. Well, it should be in radians for this formula to work. So that's your angle. I'm not sure what everybody knows here, so just bear with me if I'm repeating myself and annoying you, then skip ahead on your video. That's the pleasure of what you have with a video instead of a real live class. So 360 degrees makes a circle, so that's 0 degrees, 90, 180, 270, and you go around the circle counterclockwise, and that would be 360 or back to 0. This is also 0 radians. This is pi over 2 radians. This is pi radians. This is 3 pi over 2 radians, and this is 2 pi radians right here. So 2 pi radians equals 360 degrees. So if I want to find the cosine of some angle, here's an angle x right here. The cosine of angle x is the length this length right here, if this circle has radius 1. Okay, so we can include math.h in your preprocessor directives, and you can calculate cosine directly. But underneath there's some kind of an algorithm that calculates cosine. And it turns out that if you put a large number of radians in here, you need a lot of terms to get the right answer. So some of you in your programming problem, you just programmed this equation exactly like it is because the problem statement said include these 4 terms. Oh, it wanted the first 5 terms and it printed 4 out. Okay, so these first 4 terms, if you used it just like it is, and then calculated what the approximate cosine x is, you would have seen that if you especially if you use a large number of radians, that you would have had a really off answer. Some people wanted to make sure they could have 5 terms, 6 terms, 7 terms, 8 terms. So they turned this ugly equation into a function where the user could decide how many terms to calculate. And so that's what this little piece of code does right here. And the example I'm going to show you running this code was done by student Nick Herman. So thank you, Nick, for letting me use your example. So let's show what Nick did, because I want to show what happens, and you might have discovered that for yourself. So he allows the user to ask if you want to print out each one of those terms in the series expansion, and he calls that the verbose mode. So I'm going to say yes, I want to be in verbose mode because I want to see each one of those terms. Enter how many radians. So let's go with a small number of radians, like say 0.2. Oh, Nick, your program crashed. You must have made that be integer numbers. Okay, then hang on a minute. Let me open the program. Okay, here's Nick's program again. Enter V for verbose mode. Enter how many radians. Let's just say 1 radian. And this is how many terms we want to keep to get the answer. He has 5 as the default. But let's say we want to keep 5 terms in this series expansion. And so this prints out like this first term, second term, third, fourth, well, first, second, third, fourth, fifth term. And by the time we get to the 5th term, we're getting pretty much the exact answer of what cosine x is, if x is 1. And we can continue on. Yes, I want to do it again. Let's say I want to know 5 radians. So 5 radians, 6.28 radians is almost a full circle, but let's put 5 radians in. And for the fun of it, I'm still going to keep five terms in the series expansion. And now I'm starting to get some really crazy answers, and I'm not getting to the 0.5403. That's really what the answer is, what the answer should be. So let's do 5 radians again, but with more terms. 5 radians again, but this time we're going to put 10 terms in the series expansion. Oh, we're not quite converged to the right answer yet. We're getting pretty close. It's starting to get close here. So let's do something crazy. Let's say well, let's do it again. 5 terms, and I'm going to say 5 radians, and I'm going to say 20 terms this time. And so, okay, so after 20 terms in the series expansion, I'm actually getting the right answer now. Actually, somewhere in here, I'm getting the right answer, as you can see. If you put more digits, you would see it better. So a problem occurs. So let's say I want to put in more than 360 degrees. So I go around the circle and back around again. Well, let's actually get 6 radians. 6 is almost 2 pi. Almost a full circle. Oops. Do I want to do this again? Yes. And I'm going to watch all of the terms. So let's say 6 radians this time. And I'll say 20 terms. So 5 radians got the right answer at about here. 6 radians takes maybe a little bit longer. But if I didn't have enough terms, I will get some really terrible answers. Right? So let's put a really higher number of radians in there. Let's put like 15 radians, and let's put about 30 terms in the series expansion, and we'll look at what each term does. So, oh, things are starting to, like, look at these giant numbers in here. So maybe around the 20th term or so, 23rd term or so, we start converging to it's called converging to the right answer. So I was a little bit intrigued with how this series expansion behaves, how it blows up in these big terms, and the more radians you put in there, the more terms you have to keep before you get the right answer. So just kind of for the fun of it, I did it also in MATLAB. Now, most of you probably aren't using MATLAB yet, but what I did was allow for me to put high number of radians and how many terms I wanted to keep, and then I plotted it out so you could see what these numbers look like plotted out on a chart. So which one was this one? This was 15 radians and 30 terms. So I'm going to go ahead and put that in my MATLAB program. 15 radians. Let's see at 15 radians and 20 terms. And because I have it set up right now for 20 terms. But notice about MATLAB. MATLAB is kind of C-like. I have for loops and ends, and but what it does allow me to do is plot my data. So when I plot my data, here it is. There's the 0 that you first get. And then what happens is this data is like oscillating back and forth, positive and negative and positive and negative and positive and negative, until finally it converges to the right answer that's right here. So if I look again at what what Nick's program had, he starts out 0, 1, and then he gets this big oscillation, and yours will too, big oscillation of positive and negative numbers, and finally it settles out to the correct answer. So I can play further games with that. Let's say I want to put out 50 terms, and I want to look at the cosine of a ugly big number, cosine of 45 radians. Sounds like 45 degrees, but no, that's radians. So I have to multiply that times 360 and divide by pi to convert that into the number of degrees. But it's not a very well behaved function then, so we'll run it. And then we'll look at what the plot looks like. So it's kind of a cool plot. It starts off being pretty inaccurate in here, and then the oscillation stuff starts. It grows big, and it grows smaller, oscillates, and it finally converges to the right answer. And let's look at what happened in our C program. I'm going to do it one more time in the C program. I am going to look at each one of these terms that I just plotted. I'm going to say 45 radians, and I'm going to use, what did I say, 50 terms. Yes, 50 terms. 50 terms. And there are all those numbers very specifically plotted out, and probably having a little bit of trouble there. But the first terms are 0 and 1. It's not quite matching my plot. So, but anyway, you see you get this big blow up part in the middle. And I was just showing you by plotting it what that sort of looks like. So pretty cool. So that was a little bit just more math information about that particular problem.